Okay. Hello everyone. Welcome to Nerd Academy. This is the second lesson on April 24th. Today we will be discussing Python and the Mandelbrot set. So, first off, do either of you have any prior experience with Python? Okay. Kaka, do you? Now, about the engine we will be using, we won't exactly be using an engine. We're going to be more or less coding it from scratch. We can use engines, but that's not really what we're going for. Okay, got into it for like 5 minutes. So you do have it installed, right? Why am I getting notifications from that server? I need to set the notification settings to nothing. Okay. Yeah, I mean, engines, they're not really for the lazy necessarily. I mean, lazy people would tend to use engines more than just building it from scratch, but we're focusing on the side with computer science and mathematics. And so that's why we're not going to be using a dedicated engine, but we are using just the raw language itself. So the editor we will be using is VS Code. Do you have VS Code installed on your system? Okay, Kaka, download VS Code, install it. It's free to download and everything, easy to install, and it's a great editor, honestly. And make sure you have Python installed as well, otherwise you won't really be able to follow along.
Yeah, as much as I bring you eating NFT food. I don't like that.
Yeah, that's an extension for VS Code, but you need the program itself. Oh, from the library? No, we will not be using any libraries today. We may in the future, but today we're using pure vanilla Python. So the idea today, what we're going to do is we're going to draw the Mandelbrot set in the prompt using ASCII. Are you familiar with what the Mandelbrot set is? Okay, let me show you real quick what that is. Mandelbrot set. This thing is the Mandelbrot set. It is a fractal. It contains infinite levels of detail and is constructed with a really simple function. And I will show you what that function is and how we can draw it. Today, we are going to be drawing it in using Python with ASCII in the characters. And next week, we're going to be using JLSL to render it in shader toy so that we actually get the full image that you see here in all of its glory. And so, once you are finished installing Python, VS Code, everything that you need, then we can begin. Let's see. I'll start by showing how exactly you do this sort of thing in Python in the first place, because we need to draw something in the screen. And so we're going to do it like a square, basically. Now, one issue I foresee is that the characters on ASCII aren't exactly a square, they're kind of a rectangle. So if we want it to actually render as a square, we kind of have to squish the proportions a little bit, but it's not necessary when we begin. We'll get to that eventually. Okay. If you haven't noticed, I got a haircut since last time. Now, are you getting the actual Python software itself or the extension for VS Code? Just the, yeah, okay. So Python is an interpreted language. It takes a plain text document and then it runs through that interpreter. Okay, that's good. Yeah, that makes sense. But yeah, it runs through that interpreter, and you can do a lot of stuff with it. It's slower than most other languages, but it's very beginner friendly, which is why we're doing that first. Yeah, it's very high level, very abstract. Since it's ironic, since the Python interpreter, if I recall correctly, is written in C++, and so it's like Python is powered off of C++. And then that one's one of the lower level ones, relatively speaking. It might just be C. I don't quite remember exactly which one it is. It's either C or C++. It's probably C, come to think of it, since the math library I know for sure is written in C, so it makes sense if the whole thing's written in C. Now, Jathan, how much experience do you have with Python? Like, what's the most complex thing you've made so far? Because I want to try to avoid going over things redundantly.
Okay, I'm just trying to figure out how. I'm just trying to figure out how.
How what? How do you do it? Huh?
$500,000.
Oh.
It didn't give me enough money to buy anything at first, and it can't even work. Earlier it said this line.
Okay. But why the all caps? Yeah. Today we won't be going into the really complex stuff with, objects and classes and methods. We're going to be sticking with mostly just the basic operation of, going through the instructions one at a time. We'll cover classes and stuff in the future. But for now, the objective is just to print a little image on the screen using a bunch of numbers. And so what we'll be dealing with are strings, arrays, a for loop inside of a for loop, and then actually computing the math itself. Hey, Kaka, what is the I really don't want to call you that. What is the status on the Python installer? Okay, so, and you got VS Code set up and everything? Okay, so what you're going to want to do is you do File, Open Folder, and then navigate to some folder which you have dedicated for your workspace. I have a special folder dedicated for the Nerd Academy projects, for instance, and so I'll create a new folder called Python for all of our Python projects, and we'll have other languages in the future. Yeah, your desktop works, but not very well organized. Say, yeah, special folder. I guess that works. So, what we're going to be doing, oh boy. So, what we're going to be doing, create a new folder, a new file, I mean, and let's not start with the Mandelbrot set yet, because we don't even know what that is or how it works. So let's begin with very basic Python. So let's just call it test.py. And so let's suppose the first thing we want to do is draw something to the screen. And so we have the print instruction for that. So if we do, say, print hello world, always got to start with print hello world. Now, something to note is that it does this instruction, then whatever this instruction is, like if we did hello, or if we did like, I don't know, this is a Nerd Academy lesson, it will run this instruction first, and then this instruction, and it will do them in order. Now, once it hits the end, it'll just close. And so, usually at the bottom, I have this, just to keep it from closing. And I'll get to what this does in a bit. So if I save that and hit run, yep, hello world, this is a Nerd Academy lesson. Okay, yeah, you know about while loops and everything. Pass. So what pass does is it literally does nothing. It literally just fills the space to make the while loop valid. Yeah, and the while loop itself, you know, it runs whatever's inside of it, as long as this condition is true. And we're using true as the condition, so it's always true. Oh, interesting. Oh, yeah. Yeah, if you just input something, then you could type something in and enter, but I've always been using while true pass, since it just stops it right there once it's finished. So, this is a very basic thing. And now we can declare some variables and print them as well. So, let's suppose we declare some number. Now, the number types in Python are very curious. They're very malleable. You could have an integer, you could have a float, you could have a really big number if you want to. Yes, the number is a variable. So to define a variable, you just do the name of the variable equals and then some value. And for a number, it can literally be any number under the sun, whether it's an integer, a float, negatives, anything. Yeah, and then there's strings. We could have, there's Boolean. We could have a string. You know, we say, I don't know, dog. Be whatever we want to. Yeah, Python's very flexible. Yeah, and what's really interesting about Python is that you can do math on ridiculously large numbers, and unlike most languages where you're bound to certain data types, Python will automatically transfer between those data types. And so not having to worry about those is really nice. And yeah, we have our Booleans as well. So we could set it to true or false. And there are also object types with using classes. And an object is basically like a collection of variables and methods. Doubles and floats, those can go way higher because of how they're structured, since it's like you're defining it in terms of scientific notation. You know how you would do like 2 times, say 2.315 times 10 to the power of, 13. This would be an example of scientific notation, and floating point numbers basically use something like that, except it uses powers of 2. And every single number is between 1 and 2. And so there's a special way it stores in the binary. But when you're coding the Python, you don't have to really care about that. So we can define numbers this way. We can define strings this way. We can define Booleans this way. And we can manipulate them as well. We can indeed. So what we do for that, if we have a print statement, so let's say the sum of, and then add the stringified version of number, because you convert the number here into a string, and you can add the strings together like this, and it just sticks them end to end. So the sum of number and say, 3 equals, and then you do string of number plus 3. So if we save that and run it, you'll see, hello, this is Nerd Academy session, the sum of, oh, we've got our and. The sum of 1 and 3 is 4. That looks much more like it. The sum of 1 and 3 is 4. And so we added the number to that, converted it to a string, and slapped it at the end of the whole string and printed it. Yeah, that's a good reference. Yeah, and so you can add the numbers together and it will perform the arithmetic on it, and then you can add strings together to kind of connect them together, and that's really useful. And so then now what we can do is draw a square. We'll just draw a square over several lines. Now we also want to define a size for the square. So we could say square size equals 20. And then we will use a for loop. So a for loop, if I do for x in range 20, put a pass in there while I explain what this does. So this range function, it returns a list 0 through 19, 0, 1, 2, 3, 4, 5, on to 19. The size will refer to the dimensions of the square that we draw to the prompt. And now the reason why we're doing that is because we want to draw the Mandelbrot set, right? So we have to have a canvas to draw with. And so now normally in a for loop in other languages, you would do something like for and then I, like int I, and then I is less than 100, and then I plus plus, and then your code. Like this would be the version in Java, C++. A lot of other languages do it, like this. And it basically just takes the variable, has a condition, and then says what to do at each iteration. Python, on the other hand, it iterates the variable through a list of things. In this case, it's just a list of numbers from 0 to 20, or 0 to 19 technically, because it always omits the last one. So it's from 0 to 20 minus 1. And so this will be our x-axis. And now we need our y-axis. Technically, the y is between the lines, and the x is within a row, or within a row. And so we really need to do the y-axis first, and then have the x-axis inside of that. And we also need to define that as square size, not 20. Square size. And then we have our thing here. Did I misspell that? I think I misspelled it. Okay. So now, if we have a little print statement in here, let's say we print 0. Oh. Thought something looked funny. Okay, so if we print that, oh, something went wrong. So you see, it prints out 400 zeros. And this is because this line here just sends a 0 to the prompt. What we want is a square. So we need to define a variable. We would call it row. And row will be started off as a blank string. And then we need to add 0 onto the end of row. So row equals row plus 0. I think we could also do row plus equals 0. And then what we do is we then print whatever row is at the end of that row. So for every row going down, we initialize the string, and then for every character in that row, for every column, we add a 0 to the end of that string, and then once that row is finished, we print it, and then we repeat. So if we save that and then run it, we get our square. Oh, who left? Oh, Jafin left. I hope he comes back. I think his internet derped. Yeah, I think we should... Wait. Did your internet die? You see, while true is an infinite loop by definition, so it would never end. Technically speaking, it is possible to end if on the inside of it you have a break statement. Break will stop the loop, whatever loop it's in. So if I save that and run it again, it reaches the end of the program. Yeah, the key to exiting the loop, or do you mean how it ends? Like, when it ends the program? It ends the program when it reaches the end of the script. Since it always runs the instructions in order, once it hits the very end, that's when it stops. And so the while true loop kind of interrupts that and catches it in an infinite loop. Yeah, and so, yeah, so with this here, we now have our thing to print a square. Now, do you have your thing to print a square set up already? Okay, so you got your square printed. Now, what we can do is do something a little more interesting with it. Instead of just slapping a 0 on it, what if we changed what we printed on it based on some math? So let's say, instead of just adding 0, we added a stringified version of x plus y. Now, an issue with that is x plus y will very easily get into multiple digits. So if we run it now, you'll see that, in the early sections, it's all nice and clean. But then once it gets into like the teens, it gets really funky and it's no longer a square. So we only want the very last digit. You get what I mean here. So what we will do is x plus y modularly divided by 10. Now modular division, what it does is it's like regular division, but it returns the remainder. So modularly divided by 10 returns the last digit. Modularly divided by 2 returns a 0 if it's even and a 1 if it's odd. And you can put anything as your modulus there. So if we save that and then run it, now we got our square back. You see it's 0, 1, 2, 3, etc. And then 9. And instead of 10, we got 0. Instead of 11, we got 1, and so on. So the square is restored. And now we got a neat little pattern going. Now, are you familiar with the Pythagorean theorem? Okay, so let's use the Pythagorean theorem here to draw a circle. And instead of drawing like a gradient, we will have a 0 if it's on the inside and then a space being blank if it's on the outside. And so for that, what we can do is, well, the first thing we need to compute the distance. So if we have dist equals, x times x plus y times y, and then you take the square root of that. Oh, that's right. There's no built-in square root function in Python. So what we can do is just take the Euclidean distance for now. I believe there's a library that gives it. Let's see. Import math. Is it math? Or is it math? Yep, there it is. Yep. So math dot square root. There we go. So Now Python doesn't have everything built in automatically. Like, it doesn't have a square root built in. So this math module here does have a square root function. So we can do import math, and we have a bunch of math functions at our disposal. It is possible to implement our own square root, but it's a lot slower. Go on. Yeah, you can create your own functions. Yeah, we can do that. So what we can do is, instead of computing all this math here, we can compute it inside of a function. Now let's label all this stuff. Import libraries. Oh, that's right. Python uses the hash mark. Okay. Initialize constants. Iterate over space. Infinite loop. Let's define our function right here. Define functions. So we use def. Now what we'll do here is plot length. And so then we have our input parameters. So we'll just have, let's see, we can call these parameters I and j. And then we can return math dot square root of I times I plus j times j. And so we input I and j into it, and then it basically computes the Pythagorean theorem and then returns it. And so then right here, when we do distance equals length of x and y, then it does all the math right here and spits it into here. And then now we want to modify the row based on this distance. So if the distance is less than, say, 15, then row adds a 0. However, else row adds a space. Then we can remove that line there. And so if we save that and then run it, we will get a kind of low poly, a very pixelated looking square here. And so yeah, basically what this is doing, it iterates over the space, and at each point it gets the distance, and if the distance is less than 15, so it's inside this, then it draws a 0. We can flip this around to make it inverted. You make it draw on the other side. That's pretty neat. And we can increase the radius or the square size by a good deal. We can have a radius as well. Let's say we want the radius to be 70. So you can see if it's less than the radius now. How do I run this? Okay, so once it's saved, hit that little trash can button on the terminal right here to close it, and then you got this little run button. And wherever you have the Python file itself, you can run it. So if I were to navigate to that, where's the Nerd Academy thing? Right here, projects, Python. If I run this, it does the same thing, drawing the circle. Nothing happened, you see. Okay. Oh, there's no run button. Oh, that might be because you don't have the extension installed on VS Code for Python. So on VS Code, there's this little button here, extensions, and then you can navigate to, over to your
bed and not just make one completely out of wood.
to the Python extension. And you linked to that earlier. Right here, you linked to it. And so you can install that extension. Or alternatively, once you save it, you can just run the file directly. Okay, so there's something. Oh, you see, you still got that thing at the bottom, which adds the, on line 22. You're still adding the digit to each character, and so that's why it looks kind of funky. So it's literally mixing the inverted circle with what we did last time. Yep, just like that. Funky square with an ugly circle drawn into it. Now, if we want to offset the circle to be in the center, let's say we set the radius to, I don't know, 35 with a square size of 80. Oh, yeah, I guess it looks kind of like that. It's kind of funny, actually. Okay. So, instead of just x and y, we can do x minus half of the square size, and then y minus half the square size. That way, it will always be in the center. So, like, if it's in the center at 40, 40, and then it subtracts half the square size, which is 40, then it will return 0, 0. And so by subtracting the center, we can control where the center goes. And so when it draws our little circle. Now, it is an ellipse, and this is because the ASCII characters are not square, they're rectangles. And I can't exactly see what that ratio is. It almost looks like it's 2 to 1. And so if we were to take the y-coordinate and multiply it by 0.5. Would it be 0.5? I believe it would be. Or would it be 2? I think it would actually be 2. Multiply it by 2, and then, yep, there's almost a proper circle. It looks like it's still a little like an oval. So we'd have to see what the ratio is with one of these things. And so we can actually modify our entire thing to re-squish it back into its proper shape so that we don't get the really squished version. So if I open up GIMP over here, I can take like a screenshot and see the individual pixel dimensions of one of these characters. Okay, yeah, so let me show you what I have in here. And we have square size and radius now. Put radius right here. And I shifted the center down by half of square size. Now notice I'm multiplying by 0.5 instead of dividing by 2. This is because the multiplication is way faster and those two operations do the exact same thing. So if you can, multiply instead of dividing. So let me select one of these characters here, take a little screenshot of that, and then paste it into here, zoom in a bunch, and then I can see how big it is. So this is 7 by 17, really? That is such a weird ratio to have. Yeah, that's a really weird ratio, 7 by 17. Actually, it's not that weird because there's probably 1 pixel spacing between each character, top and bottom. So it's more like 6 by 16, but it's still 7 by 17. So then, if we head back into here, what do you see? Can you take a screenshot of what the actual thing generates? Oh, I don't see anything. Oh, scroll down a bit. See if it's visible then. Nothing's there. Oh, and you're doing if the distance is greater than the radius too, so it should be visible everywhere, shouldn't it?
That's correct.
So nothing there if you scroll up or down? Oh, did you hit the trash can first on the thing? Because you gotta dump the current terminal and reopen it in order for it to refresh itself.
That'd be perfect because I just got them two of the sticks.
Hmm.
Yeah. Huh. Good timing.
Okay. Everything here looks perfectly fine. It looks identical to what I wrote. Try running the actual file itself from the File Explorer and see if that changes it. Looks like the formatting is gone again on that screenshot. Because in the last one you sent, it had all the formatting. Or like the color highlighting. Okay, that's kind of odd. Okay, so now we can implement the actual ratio here. So instead of multiplying by 2, we would multiply by 17 over 7. Now if we save that and then run it, now we get what appears to be a proper circle. So if I screenshot that real quick, bring it into GIMP, we can see if it's actually a proper circle. Measuring the pixels here. Just measure it, see how close it is to a proper circle. Yep, this is a circle. Okay, that's great. So we just multiply whatever our y component is by 17 over 7, and then we'll get it. So we can actually define 17 over 7 as a variable, so we don't have to calculate that division every single time. So we could call it aspect ratio equals 17 divided by 7, and then just multiply the y by aspect ratio. Voila. Okay, now for actually doing the Mandelbrot set. So have you followed along so far with everything? Like you haven't fallen behind or anything? Okay, that's great. Okay, yeah. Yeah, everything looks great. Yeah, and your code looks very much like mine, which is great. So for this, we will create a new file, and we can use this one as a reference. We will call it Mandelbrot set.py. That's Mandelbrot for Mandelbrot. That's a guy's last name. He's basically the guy who discovered fractals. Now, for context with what this is or what it means, are you familiar with complex numbers? Or imaginary numbers? No? Okay. So, to introduce what that is, I'm going to head over to Desmos, and you're obviously familiar with the square root function. You know, like the square root of 2 is about 1.414, square root of 4 is 2, you know, and so on. However, you may notice that there's no negative values. Now, it's interesting because the square root is just the square function, but it's mirrored around this green line. Now, if I have another function like this, like that, you can clearly see that the red and the blue one are just mirrored around the green line. And when you mirror something around the green line, you're switching the outputs and inputs with each other. And you may notice that no value of x squared returns a negative value. There's nothing down here, which means that the square root function, there's no value down here. So if you do square root of -1, we get undefined. And you could see how that would be a problem, right? Because what should the square root of -1 be? And there's actually a reasonable solution to that. So if we were to define a variable I as the square root of -1, don't worry about that. Desmos just doesn't have anything for how to treat this. Yeah, imaginary number, I. And is this ringing any bells at all for what this means, or is this completely new to you? Okay. So, okay, so where to go from here? So, if I is equal to the square root of -1, then I squared is equal to -1. And so, if we have I as something, if we have, say, 2 plus I, well, we can't really add them together because, I mean, we don't even really know what I is. It's just kind of this thing floating up there. And so if we just treat this as a whole idea, this is called a complex number. When you add a regular number, called a real number, to an imaginary number, we get a complex number. So it's imaginary right here. And we can put complex right here. Yeah, and so we have this whole new world of mathematics from this simple idea that we define the square root of -1 as something. Now, how to really visualize this? Well, on Desmos here, we got the x-axis and we got the y-axis. So if we label the axes to the real numbers and the imaginary numbers, well, then we can draw the real number here and the imaginary number here. So 2, 1 can be drawn as 2, 1. So this point here would be 2 plus I in the complex plane. See what I mean? And so it's kind of like the coordinates in this space. Are you familiar with vectors at all? Okay, and we discussed vectors on last week's session. And so a complex number is a lot like a two-dimensional vector. And so you can add two complex numbers together. So if we got that 2 plus I, and then we add, say, 5 plus 3I, what on earth? Who's talking to me? So if we have 5 plus 3I, and then add it to 2 plus I, that turns into 5 plus 2 plus I plus 3I, or 7 plus 4I. And so then if we draw 5, 3, and then we draw 7, 4, you may notice that this one plus this one equals this one. And so that's pretty straightforward, adding them together. Yeah. Now, what if we want to multiply two of them together? That's where things get interesting. Let's color these a little different. Let's color them red and blue. Let's call them A, B, we'll call this one sum. Have a folder called sum. Just slap those in there and close that. Now if we have a folder called product, we want to multiply A and B together. So we get 2 plus I times 5 plus 3I. Now what we do here is just like we would with any multiplication. So we have to expand it out. So we copy this and then multiply each of the terms inside by it. And then we repeat the same thing. So we get 2 times the 5 and then 2 times the 3. And then the same thing right here. We get I and then I times I, or basically just I squared. Did you get that with how this is being expanded out? Okay. And then obviously 2 times 5 is 10, and 2 times 3 is 6. We can remove those parentheses, and then those are just multiplied by I. Now 6I plus 5I is just 11I, and then we have this I squared. Now you may remember that I squared is just minus 1. So we can replace I squared with minus 1 to get minus 3, and 10 minus 3 is 7. Would you look at that? We have a new complex number. We have 711 as the product. Way up here. Isn't that cool? So yeah, and now that we have this set up, we should be able to drag around A and B, shouldn't we? So if I call that A and call that B, the sum, we can expand this out using A and B instead of these constant terms. So if I do AX, BX, and then AY, BY, this grabs the first component of A, or the 2. This grabs the second component of A, or the 1. And so that's how we can kind of do math on them. And then we, expand all that out again. And, it's really just AX plus BX, and then AY plus BY. And so then if we drag those two around, we're adding those two together. So now we can move them wherever we want to. So then the next thing to do is to do the product in the same way. So we get AX plus AYI plus times BX. Oops. I made a silly. There, that's better. Yeah, it's supposed to be this term times this term here. And so then we can expand it out just as we did before, where we take that, you multiply it into these, and then you take that and you multiply it into these. Same thing with right here. And then so we have AX times BX plus AX times BYI, and now this I should be right here, and AY times BXI plus AY times BYI squared. So we close out of those things. You have two I terms here. So we put parentheses here, drag the I out of there. So we have the complex term. This obviously becomes negative. And then we drag that over here, close these parentheses. So we got this. And then what we can do is replace the terms in our point with this thing. Grab what's inside of it. Nope. Now we have our product. Ah, you see, and isn't that interesting? Look how the product moves around. Isn't that weird? Yeah, and so it moves around in really weird ways. Now, suppose for a moment that our numbers were real. They were glued down to the real number line. Now let's change these to only be able to move along the real axis. Now you may notice that these are just regular numbers. So if I have 2 and 3, well, their sum is 5, their product is 6. If I have 2 and 5, their sum is 7, their product is 10. 3 and 5, sum is 8, product is 15 over here. And it's like the complex numbers are a superset of the real numbers right here. And so all of the arithmetic we're used to works just fine using the complex number system. Isn't that something? Yeah, so let's bring these back into our complex plane here. Now, there's a nice intuition to think about here. So if we set A to 1, just 1, 0, just pure 1, you may notice that the product is always following B, and the sum is always 1 to the right of B. Now, if we move point A around a unit circle right here, if we move it to, like, say, right here, let's say we set it to pure I. If we set it to pure I, you may notice that the product is now just a 90-degree rotation of wherever B is, right? Yeah, and so we can change what that angle is by moving A around this circle. It could be a 180-degree rotation for -1, or a 270-degree rotation here, or any rotation that we want. And then if we move A around, further away from the origin, so does the product move further away from the origin. So we're really changing the angle and magnitude of how it offsets from B. And it works in reverse too. If we put B on the unit circle and then A out and about, then it does the same thing. And so the relationship that they have is really interesting. And there's this weird rotation mechanic going on, isn't there? Because, we can rotate it and we can kind of exaggerate it around or, change the amplitude. And this is a really powerful system if you need to deal with like rotations in two-dimensional space. By defining everything as complex numbers, you get this simple little formula, and you can input your complex numbers, and it just spits out a rotated vector. And this is useful for so many things. So, did you get all that so far? Okay, that's great. So now, okay, yeah, write all this down so you can follow along. Since, the whole point is getting this in your brain. Oh yeah, that's good. Writing things down on paper is excellent. Yeah, and so really you just gotta look at this formula here. AX times BX minus AY times BY. Now notice how on the real part, it's the X components together minus the Y components together. And then on the imaginary part, it's the X and the Y, and then the Y and the X. And so there's this nice symmetry to it. So then, okay. Did you get all that written down? Okay. Now, how does this apply to the Mandelbrot set, is the question. So, this is where it gets interesting. Say we have a function. Well, not really a function. It's a function, yeah. So, it's a function that will take in a complex number and spit out another complex number. So, it's like a regular function, but it's taking in a complex number instead. And, say we have a constant c, and we can put it anywhere we want to. Let's color it green. Say we have a constant c that starts somewhere. And then we have a function. f of z equals z squared plus c. Now z will be a complex number, and c is also a complex number. And so what we do is we initialize z as 0, right in the middle. And then we take this function. We should actually turn it into an event. So we could do f equals, and then z, and then our little arrow, and then the arrow for an event. And we can call z, well, we need to start z off as 0. Or we need to define it first. Okay, so we got z here. Now, for this event thing right here, what you do is a hyphen, and then this symbol here, the is greater than symbol, and that turns into an action, I think it's called. And so, let me make this not draggable. It's a feature of Desmos where you click this button. Why is oh yeah yeah, so when you click this button, wherever we put z, you click this button, goes back to the origin. And the last lesson used actions like this extensively, and it's kind of like in the Python code how we do something to a variable. That's what these actions do. Now, obviously, this is a complex number, so we can't just square it. Desmos is yelling at us about that. So what we can do is take this thing here, and which is a number times another number, complex numbers, and then apply it to z. So if we replace that with that, and then replace all these references to our z variable, isn't that interesting? Now, zx times zx is just zx squared, and zy times zy is just zy squared. So it looks a lot cleaner now, doesn't it? Oh, and also, zx times zy plus zy times zx is just 2 times zx zy. And so when we square something, it becomes a lot simpler. So now, if we have, let's turn those off real quick. Here, let me create a folder and put all that stuff in there. Parameters. Just kind of shove those in there and turn it off so they don't display. So let's say C is somewhere. If we run this event right here, or this action, it goes straight to C, since it squared 0 and then added C, so it's right over there. Then we run it again, and now it's over there. So it squared this number and then added C again. So the square of this number is what? What is the square of that number? So if we put these two right over here, so this is the square of that number, and then we added C. So that's why Z ended up there. And then we can, what we do, we can take A and B, bring it back to where Z is now. So my guess for where Z will end up next is right around here. So if we run that event, boom, right there. Because see, it squared it, and then which turned out to be this, and then it added C right there. And then we can keep running that, and oh, it's starting to get further away. So if we keep on running that, it just gets further and further away. Okay, what do you need catching up on? Okay, writing it down, yeah. So yeah, when you take that complex number and you square it, it becomes, like the expression becomes simpler. Because this is if you're multiplying A and B together, and this is if you're squaring something. Since you're multiplying it by itself, a lot of it simplifies down, you see. And so what this function does is we take this, we square Z, and then add some constant C to it. And, you may have noticed this behavior. If you just click it a couple times, Z shoots off into the wild blue, never to be seen again. Because if we just keep spamming this, I mean, look how big these numbers are after a couple iterations. These numbers have 124 digits after like a couple clicks. Isn't that massive? Yeah, exactly. Now, what if we put it right here? If we put C right here, what happens? Let's spam click it. Oh, would you look at that? Stop somewhere. Oh, and that isn't that weird? We keep spam clicking it, and it does nothing. It's slowly getting closer to some point. Now, what was special about this number here? Let's suppose we, I don't know, put it right here. If we put it right here, reset Z, and then spam it. Oh, it shot out again. Number with 274 digits. Uh-oh. Something went weird there. What if we put it like around -1? And then we spam click it. Oh, well that's weird. It's iterating between 2 points. Going back and forth. And it's stuck there. Isn't that weird? And it's weird because, like, everywhere you put this point, it behaves a little differently. Like, I think right here, what does it do if it goes right here? Yeah, it goes like a weird little spiral, and it slowly approaches a point. And just spirals down. And there's so many points that do this. Now, are you curious at all? What is the rule governing this? Like, what is causing this to happen? Yeah, and we want to see, like, you know, how can we visualize this? Now, I believe I have a Desmos graph. Let's see. So say we use this one. Okay, so I imported an image here. Now, do you see that? So those black dots represent all the iterations. Like, you know, it goes there, and then there, and then there, and there, and so on. And so if we move that around, it's really chaotic. But if we move it into here, it's stable. And it approaches some point. If we move it into this little circle here, it iterates between, it's in a cycle between 3 points. Right here, it's a cycle between 2. If we move it anywhere outside, it explodes and is absolutely crazy. You know what's really weird? There's a little tiny blue spot right there. So if we bring it right in there, suddenly it's stable again. You know, isn't that freaky? And so, yeah, if we put it on the blue, it's stable. If we put it outside the blue, it's crazy. And so this here is the Mandelbrot set. It is the set of all numbers where it's stable. And so what we're going to do is we're going to draw this shape in Python using that little square thing that we did. So all we got to do is compute this function here and repeat it many, many times and see, did it explode out into the wild blue, or did it remain mostly stable? If it remained stable, like if it's within a circle of, say, radius 2, if it's in a circle of radius 2, then we can color it, or we can draw like a 0 on it. If it's out in the wild blue, we can draw a space. Does that make sense? Yeah. So yeah, that's what we're going to do here. So let's head back over to Python. So we're basically going to be doing the same thing here. Star. What's star? No. Okay. So we can basically copy all this code and bring it into here. Now we're going to be changing all of the stuff here. So let's remove all the stuff we don't need. So we keep the stuff with the row code. That we keep. All the stuff about the actual computation, that is what we change. So we need to initialize, so at each of those points, we need to run this massive, iterating function, basically. We need to run this thing many, many times. Now, first thing we need to do is decide how many times we want it to do it. Let's say 100 times. So we could set iteration limit equals 100. And so then, for each of these, pixels here, we can run a function, and we'll call the function def Mandelbrot. And let's see, what should we take as an input for this thing? Probably the coordinates. We'll do R for real and I for imaginary. And then iteration limit is a constant. We should probably define the function after the constants. And then we have a for loop for iteration in range iteration limit. That way we run the code that many times. Now we have to we also got to define C somewhere. That's right, because Z is always initialized at 0, and then C is wherever the pixel is, because C is wherever the pixels are on our little screen, and then Z is what actually starts off as 0, and that's what we're actually reading to see where it ends up. Does that make sense at all? Okay, you might be talking a little fast for this. So, the first thing we want to do with actually no, we don't want to do a for loop. We want to do a while loop. While iteration is less than iteration limit. We do not want a for loop because we're going to be breaking this thing at any time. And, this is just nicer. So, while... Oh, it has to be defined first. Okay, iteration equals 0. So then, iteration equals 0 while iteration is less than iteration limit. Obviously, we want to, add 1 to it to increment it. And then we got to square our number. So if you recall from our little thing, when you square a complex number, you square the x component minus the square of the y component, or the imaginary component, and then 2 times the real part times the imaginary part. And so we write that down. So Z also has to be initialized. Let's see. We should probably use a tuple for this, because, already there's like a bunch of numbers flying around and we got to organize this thing. So to keep it organized, right in here, we will initialize C, we'll do capital C, equals a tuple, which is x and y. What? Okay, maybe lowercase c. So lowercase c is equal to x and y. And then z is equal to 0, 0. Now, maybe we won't bring in r and I then, but instead use these tuples. Now, a tuple is interesting. You just got these little parentheses and you put these numbers in them. You can put numbers, strings, booleans, whatever you want in them. And you can even have as many entries as you want. You can have unlimited entries. But we're going to be using 2 entries in our tuple. And these tuples will represent these complex numbers. And so what we want to do then is run the Mandelbrot function. Mandelbrot. And then feed in C. Now instead of taking R and I, we'll take, we call that C as well, but that might cause some issues. Oh, no, it won't cause any issues. Okay. So then initialize the iterations, and then while the iterations is less than the iteration limit, add 1 to that. Now, we don't need to initialize Z out here. We want to initialize that in here. So then it takes in the c value, initializes z. So now we need to modify z. So z is equal to z, is it z dot x, or is it, I think that, yeah, that's how you do it. So then times z0, and then you do plus z1 times z1, or the square of the real part minus the square of the imaginary part. And then for the imaginary component of this number, we do 2 times the real component times the imaginary component. And then we also have to add c to both of these things. So, do you get that? Okay. So yeah, we at each pixel in our little square thing, we define c to be equal to the x, y pair. And then, we're going to want to transform that actually, because remember, this square is 80 by 80. And if you remember, this image here is really small. It's like all contained in a circle of radius 2. And so we're definitely going to want to transform our pixel coordinates in order to, kind of fit in here. Okay, so next thing we want to do is modify these x and z coordinates to, be of a maintainable size. So if it's 80 by 80, what we can do is it should be proportional to the 80. If our image is 2 by 2 in the mathematical space, then we need to transform it. That's not 2 by 2, it's 4 by 4, centered at the origin. So we need to multiply by 4 and then divide it by the square size. So we need to multiply by 4 and divide by square size. And then we need to subtract 2 that's centered on the origin. So you multiply by 4, we divide by the size of the square, thus transforming 80 into 4, and then we subtract 2 so that it's nice and centered and we can see what we're doing. But another thing we gotta worry about is, so x increments properly, but y, see in the mathematical space, the y-axis, as you move up, it increases. But in our space, each row, as you go down the rows, it increases. So we have to flip y around. So y needs to be inverted. So we can do square size minus y to kind of flip it around. That way 0 becomes square size and square size becomes 0. Does that make sense? Okay, well, either way, this here will flip it around because it's the square that we had before where we drawn the circles is kind of flipped upside down. So if I go back to this one and draw it, this one has the greatest y value and this one has the least y value. And as you go down, the y values increase. But in the mathematical space, the greater y values are up instead of down. And so that's why we had to add this little bit of code here to flip it upside down. Because it was already upside down, so we got to flip it back upside down to bring it back to normal. So that's how we initialize the constant. We go through all the little pixels on our screen and do that to it, to scale it and bring it into our mathematical space. And then we run our Mandelbrot function. Now, our Mandelbrot function, it initializes the iteration as 0. You can probably define iteration limit inside of it. And then we initialize z as the setter. And then we get into the actual while loop here, where we add 1 to iteration. Then we modify z. Now comes the important part. We need to see if z has shot out into the open blue. So what we do is we do the same thing that we did in our last theme where we grabbed the length. So we can grab this length function that we got last time, bring it into here, and then we can test if the length of our value here has exceeded 2. Now, we're doing this a lot of times, so we don't want to square root it. So we will use the, we're going to use the Euclidean distance, the squared distance, basically. So if the length has exceeded, if the length squared has exceeded 4, or basically it's outside of a radius of 2, then what we want to do is break. Stop, exiting the loop, exiting the while loop, and then we return iteration. And this is where it gets real interesting. So then we can define iterations right here as equal to our Mandelbrot function. So our Mandelbrot function basically just sees how many iterations until our number blows up. Do you get that? Okay, so then now we have that. So now we need an if statement to draw to our screen. So we can head back over to our test file, grab this code, which we used to draw the zeros and the spaces, slap that there, and then modify it. So if iterations is equal to the iteration limit, oh, and that's why we got to define the iteration limit outside of the function. It's got to be global. So yeah, if the iterations is equal to the iteration limit, then slap a 0 on it. Otherwise, slap a space on it if it's outside. So if it's stable, it will reach the 100th iteration and it's still stable. It's still contained. So we draw something there. If it exploded, then it draws a space there instead. And so this should be it. So let's see what happens if we run it. Aha! Now isn't that neat? Right there. We got our Mandelbrot set. Yeah, see, it's the same shape. Now, I just noticed that this is really squished. I forgot to apply the aspect ratio to it. So, right here, where would I apply the aspect ratio here? I would apply it, I would put all that in parentheses and multiply aspect ratio by that. Close that, run it again. That's more like it. Although it's really squished. It's really, really squished. Let's crank up the size a little bit. What if we made the square size, I don't know, 200? Let's hope it doesn't roll around. Yeah, that's more like it. We have drawn the Mandelbrot set in Python prompt. Isn't that epic? So, how far along is your code relative to what I have written? Like, were you following along the entire time, or? Okay, so then when you run yours, you see the Mandelbrot set? Okay, let's see what your code looks like. Okay, so I'm not sure what AST is right there. Okay, so define Mandelbrot with C, and then I see the issue. In the Mandelbrot function, you don't return you don't check the distance thing like I do, and because you gotta check the distance using the length function, which I brought in, and break the while loop if it has, and then return iteration. And then down there, you're defining Z in the wrong space. Like it's, I kind of shuffled things around. You might not have been looking when I did, and so you can see the difference between mine and yours. Like I initialized Z in the Mandelbrot function. I initialized C right here. You initialize C a little bit differently than I do. And then I define the iterations to the output of the Mandelbrot, which is grabbed, return, sends out the output, and it returns the number of iterations. And then it slaps into here, and then if it's equal to the limit, add 0, else add a space. So yeah, you can have a look at this and modify your code to kind of match up with it. Here, let me send a screenshot of the code that I got. That way, if I go somewhere else on my stream, then you can still see it. It does, but if you copy paste it, it's better if you type it out. That way you consciously perceive each individual piece of the code so you can process what it all does. Because if you copy paste, then who cares what's in it? You know what I'm saying? Yeah, you followed along really well. It's just the things that were kind of goofed were when I was kind of talking too fast and going here and there. That's something I need to get better at. Yeah, and so Z is initialized inside of the Mandelbrot function instead of in the for loop, and then you got to check the magnitude of Z to make sure it has not exceeded the limit. So now that means that you have like an if statement or a while loop or something where you don't have a colon. Okay, see, in Python, whenever you start a thing where you need indentation, you need to have a colon to kind of initialize it. And it even tells you where it is. So on line 16, and in the 30th position. So it tells you exactly where it needed a column to be. Or a colon to be, not a column. It tells you exactly where you need a colon to be at. Okay, so this is because, okay, let's see what's going on here. You got while iterations less than the limit, add 1, then do that, and if the length is greater than 4, break, return iteration. Okay, so that looks identical, yeah. Okay, and then, okay, so then it didn't draw because in the for loop, notice right after I initialize C, I set iterations to be equal to whatever the Mandelbrot function returns, and then I check if it is equal to the iteration limit or not. And so on the screenshot that I sent, that code is, I should really include the lines on my screenshot. In my code, it starts on line 29, where it sets iterations to Mandelbrot of C. And then on line 30, if iterations is equal to the iteration limit, it slaps a 0 there. Otherwise, it slaps a space there. Yeah, and so the reason why it's not showing up is because you're literally not drawing anything at all. Like, it's doing all the math, it's just you're not putting anything on the screen. Oh, yeah, that would do it. Yeah, and once you get that up and running and actually displaying it, we're going to modify how we display it a little bit to introduce a gradient. And it's going to look really cool. Where are you at right now with it displaying? Okay, so oh yes, you have to initialize the z value. Yes, it seems you don't do that in your Mandelbrot function. See, in my Mandelbrot function, I initialize z as 0, 0. And you see, whenever an error appears, it tells you exactly what went wrong. So right there, local variable z referenced before assignment, which means that you got to define z somewhere, because you tried to use it without defining it, and that's not allowed. So you got to define it first. And so on your code, you would put it right on line 12. Yeah, you gotta define it like that. Okay, yeah, it is. It's declared in the right location. And you're still getting this error from this form of the code? Like, did you save it, trash the old terminal, and then run it again? Now, what was happening before where you're running into a weird error like that and all the code is correct? Like with the circle. Did you like reload VS Code or something? Because you seem to have had that issue. How weird. But see, if you can't run it from the terminal, just execute the actual file that you're writing to, because you won't get any goofy stuff like that when you're doing it through there. Like if I run mine, Mandelbrot set, it renders the Mandelbrot set just fine. There's something. It looks like you rendered the Mandelbrot set, but really tiny. Let's see. Yeah, you did 4 times square size. But how to get that small? Oh, you're rendering it with square size is 20 on yours. I set my square size to 200, which is why it's so small. So set it to 200 and then run it. Maybe just hit the X button on the terminal. Maybe it's that while true thing at the end. If I remove that and then run the terminal. Now I still have the thing. It's real odd. I think there might be some setting or something weird going on preventing it. In that case, just run the file from the source then. From wherever you have the actual Python file located, just execute it directly. Haha, there you go. You got your Mandelbrot. Look at the level of detail on that thing. Did you have it on a value higher than 200? Oh no, it's the same. Yeah. And the interesting thing about that, all that detail that you see, there's an infinite amount of detail if you zoom in enough. And it's quite astonishing. So the next thing we're going to do, and this will be the last thing for today, instead of just coloring it with zeros and spaces, we're going to color it a little bit differently. So you may have noticed with this thing that when it's crazy, some places like this, it stays stable for a good amount of time. Versus other places get crazy really quickly. Other places stay stable for longer. Do you see? Like this one, it stays within, regular bounds for a while. But then over here, it's like, So what we're going to do is we will render a space on the inside. And then on the outside, we're going to render a stringified version of the iterations modularly divided by 10. So we're taking the last digit of the iterations and then drawing that. And we'll see what that looks like. Aha, now we got some. No, so we're spanned with a bunch of ones. There's some twos here. But then look at all these numbers and how they're kind of propagating around the shape. Isn't that something? And, like right here, okay, so yeah, out here it takes one iteration out here. Then it's 2 iterations, and then 3 iterations, and 4, 5, 6 iterations, 7 iterations, 8, 9, and so on. And as you get closer, the numbers start to get more chaotic because the number of iterations it can last gets bigger and bigger and bigger. And if you zoom in enough, you get to points where it's 100,000 iterations, 1,000,000 iterations, 1,000,000,000 iterations as you get closer and closer to the edge. And there's no limit to how big the number of iterations can get. And you may notice, it's kind of like there's like a weird outline. It's like a curve, a curvy shape here that divides the borders between the 3s and the 2s, for instance. And so it's such a tiny little change right here to draw the iterations instead. So, you draw a space right here, and then you draw, the stringified version of iterations modularly divided by 10 if it's outside. And that's really cool. And, that lets you see the gradient. Do you got that typed out? Okay. Nothing at all. Oh, first off, on line 33, it should be at a space and not a 0. But how do you mean? Oh, on line 33, instead of adding a 0, you should add a space. That way it's like hollow on the inside and not filled with zeros on the inside. But other than that, everything looks right. Maybe try running it through the... Aha, there we go. Okay. So now we got something. Yeah, isn't it? It's such a cool... Yeah, that thing's really cool. Just wait till you get to the JLSL next week. Because with Shader Toy, we can render the images in their full glory like this, and even better. You know, with perfect pixel precision, and we can control the colors on each pixel so we can draw whatever images we want. And so that's what we're going to tackle next week, is drawing the same picture but in that. And, you know, there's other techniques that are used over there, but the math is still the same. And to think that this cool image is just purely from raw mathematics. So, that will conclude this Nerd Academy lesson, April 24th. And the project for this week will be mess around with this. Instead of just having the C value be each pixel, suppose the C value was constant, and the Z value, where it initialized, is where each pixel is. See what kind of images you can draw there, and see what happens if you initialize Z somewhere else that's not the center, because each of these different combinations produces a different image. And there's infinitely many of these pictures here. Oh, yeah, that's what happens when it rolls over to the next line. The canvas isn't big enough. Still looks cool, though. Oh, yeah, that'd be nice. Don't worry. In Shader Toy, we will be able to zoom out all we want. So, yes, this concludes the lesson. Shader Toy, its code is written in JLSL. And that's a graphics language. And just like I showed you Python, I'll show you JLSL. Yeah, so, for real this time, that concludes Nerd Academy. I will see you next week.